All right, so now I'm going to prove local convergence of the geometric Newton method for vector fields. And so in particular, I'm going to show superlinear convergence, and in particular, at least quadratic convergence. So let me sort of just recall that the notion of superlinear convergence actually the notion of sort of quadratic convergence on manifolds does not depend on the choice of a Riemannian structure, for example. On sort of any additional geometric structure on the manifold. Whereas in contrast, if, for example, we were just trying to prove linear convergence, you would actually need to pick say a Riemannian structure inside a manifold. Okay, so we're not going to make any. So in light of this observation, all right, which we discussed as previously, we're not going to make any additional assumptions on the manifold. So let me first state a lemma. Okay, so let these double bars, right, be any consistent norm on R n by n, okay, such that the norm of the identity operator is just 1, right? So if the norm of some operator E is less than 1, then the inverse exists. Oh, sorry, actually 1 minus E, the inverse of that exists. And we have a estimate on the induced operator norm, right? It's going to be less than equal to 1 over 1 minus the operator norm of E. Okay, so if A is non-singular and A inverse acting on B minus A is less than 1, then B is non-singular. And you can again get an estimate on the inverse of B in terms of the norm of the inverse of A and this thing here. Okay, all right, so with that in mind, let me now state the theorem. So this is the local convergence of Newton's method. And so under the requirements and assumptions and y notation of the geometric Newton method, right, we assume that there exists a point x star exists some x star on the manifold such that, okay, the vector field vanishes at x star, and the Jacobian at x star, the inverse of Jacobian exists. Okay, then there exists a neighborhood U of x star in the manifold M such that for all initial conditions x0 in U, right, the algorithm, the geometric Newton algorithm, generates an infinite sequence xk that converges superlinearly. So in particular, at least quadratically. To x star. Okay, so that's the statement of the theorem. All right. So actually, I'm going to copy these estimates into a corner here, so I can erase this. Okay, so if the norm of E is less than 1, then I can have this induced operator norm on the inverse of 1 minus E as less than equal to 1 over 1 minus the norm of E. And then if A is non-singular and the norm of A inverse applied to B minus A is less than 1, then B is non-singular, and I'll sort of just denote that by an estimate on the operator norm here. This is less than equal to operator norm of A inverse divided by 1 minus the operator norm of A inverse applied to B minus A. Okay, all right, so those are sort of the essential results from this lemma here, so I'll just go ahead and erase it. I'll start the proof. All right, so let's start the proof of the local convergence of the geometric Newton method. Okay, so let's say we have a coordinate chart. And then we want that the sort of the zero, the vector field, to be in the domain of definition. Okay, then to prove quadratic convergence, right, so it's sufficient to show that the image of the sequence iterates, which is contained in RD, converges quadratically to the image of the zero of the vector field. Okay, and then to simplify notation, right, we're going to denote the coordinate expressions with the hat. Okay, so as an example, xk hat then is just the image of the point xk by the coordinate map. Okay, for example, all right. Other examples include if you have C xk hat, this is the sort of the derivative or the linearization. It's like of the coordinate map applied to the vector C. Right, you have that. Well, right, that's one case. That's another one. That j hat xk hat is equal to this. Again, the linearization of the vector of the coordinate chart composed with j xk composed with this inverse. Okay, and r hat x hat, it's like for some vector is equal to just the coordinate function applied to this. Okay, so note that this Jacobian j hat xk hat is a linear operator. Okay, from Rd to Rd. Okay, so that's a D by D matrix. D by D matrix. Okay. And then the other thing is that this coordinate representation at the retraction inherits the property that of the rigidity property, it's like of the retraction, and the way it manifests itself is that the differential of this at the identity is the differential of this at 0 is the identity. Okay, so r hat x hat, right, is a function from Rd to Rd, whose differential at 0 is the identity. Okay, so again, it's like what we're trying to do is to write everything in local coordinates with respect to a coordinate chart, which contains the distinguished point x star, which is a 0, the vector field, and then the fact that R is a retraction, it's like manifests itself when you take the derivative of this function from Rd to Rd. It's like at 0, it gives you the identity matrix. Okay. All right. So with that in mind, then we're ready to talk about the geometric Newton method, in particular what the algorithm looks like. So the geometric Newton method has the following update, right? That you can write xk plus 1 as the retraction based at xk. Okay, let me just put everything in coordinates, so there's a hat above everything. Okay, applied to minus j hat. So I'm going to invert the Jacobian, if you will, okay, in this definition here. J hat xk hat inverse applied to the vector field, or the local coordinate expression for the vector field at the point xk hat. Okay, so I'm sort of putting everything, it's like into this one single expression, and I'm going to analyze this sequence which is generated. So this is in contrast to the, or let's compare it, if you will, to the classical Newton method. So why can I apply this classical Newton method? Because of course, let's see, right? We have this local coordinate expression for the vector field, and we could try applying the classical Newton method to that instead, right? So if you have C hat, which is a map from RD to RD, right, and you apply the classical Newton method to that, right, sort of yields the following. X hat, xk plus 1 hat is equal to xk hat plus minus the differential of C hat xk hat inverse applied to this. All right. So what is the idea then? Okay. So the idea, if you will, is to compare the geometric Newton method sequence with the sequence which comes from the classical Newton method applied to this coordinate representation of the vector field. Okay. So the strategy is to show that the two sequences are sufficiently close that geometric convergence of the classical Newton method implies the sort of quadratic convergence of the geometric Newton method. Right, so that's basically the proof strategy is that we're going to compare the sequences, the differences between these two sequences. Okay, so and as you might expect, that's the reason why it's like we're going to take advantage of this lemma. It's like which relates sorted inverses of two different operators. Okay. All right. Okay, so so I'm going to let beta be the operator norm of the inverse of the Jacobian operator in this local coordinate chart. Okay, so since the vector field is smooth, it follows that that the Jacobian is smooth as well. Okay, so basically one consequence of that is that you have a Lipschitz estimate. Okay, exists some rj greater than 0 and gamma j greater than 0 such that the difference in norm between j at x hat minus j at y hat is less than equal to this gamma j times the difference, the distance between those 2 points which you evaluated at. Okay, and this holds for everything in a ball of radius rj. It's like about the point x star. Okay, this is true for all x and y, right? Or x hat, y hat, which are in the ball of radius rj about the point x star. Okay, then you let epsilon be the minimum of rj and 1 over 2 beta gamma j. Okay. All right. So now we assume that xk hat is in this ball of radius epsilon, right? Epsilon is given by this, right? X hat star, right? Okay, so again, it's like if this thing is to converge at all, right, it has to be such that after a sufficient number of iterates, right, it will be in a ball of any positive. So, okay, so put another way, it's like if this sequence is to converge, it's like to x star, right, it has to be that for any ball of finite radius, right, there's going to be some big k for which all the iterates, it's like, will be within that ball, right, once little k is bigger than big K. All right, so we're just going to assume that. So then it follows that so now I'm going to sort of look at something like this, right? So I'm going to show this condition holds, right? So it follows that j hat x star inverse applied to j hat. Okay, so I'm just looking at these two points. One of them is going to be x star and the other one's going to be xk, right? J hat xk hat minus j hat x star hat. Okay, all right. So I'm going to need to show that this thing is less than 1. Okay, so this is less than equal to the norm of j hat x star inverse j hat xk hat minus j hat x star hat. Okay, all right, but we have an estimate for this. Okay, so this is less than equal to, okay, so this is beta, right? Okay, and then this thing is less than equal to gamma j times the distance between xk hat and x star hat, but xk hat is in the ball radius epsilon about x star hat. Okay. So this is going to be, all right, so let me just put that first, right? So that's xk hat minus x star hat. Okay. Okay, and then this is again contained in a ball radius epsilon, so this is less than equal to beta gamma j epsilon. Okay, but we've chosen epsilon to be the minimum of these two things. Okay, so this is less than equal to 1/2, right? Because epsilon is sort of then. Okay, so it's smaller than or equal to 1 over 2 beta gamma j, right? So that gives you the 1/2 there. Okay, So now I can evoke this lemma, right? So A, so another way, A is j hat x star hat, sorry, right? And then B is j hat x star k. Okay, all right. So this is the lemma. By the lemma, we have that we now have an estimate on the inverse of the Jacobian at the point xk hat. Yeah. So j hat xk hat is non-singular, and the operator norm of the inverse is less than equal to the operator norm of the inverse at the point where the vector field vanishes, okay, divided by 1 minus this operator norm. Okay, right, which is less than equal to, okay, so this 1 minus half, right, that's a factor of 2, so it's 2 times the operator norm of the inverse. Okay, I don't really need the parentheses there. Okay, but the operator norm of the inverse is beta, okay, so this is actually equal to 2 times beta. Okay, all right. So what that means that is that basically you can actually define the well, you can actually solve, if you will, it's like the Newton equation, right? It's like that inverse is well defined, right? So you can solve the Newton equation. So let me just state that. So this means that okay, maybe let's add a few more things to this here. All right. So beta is equal to the norm of j inverse, or j hat x star hat inverse. Okay. Then epsilon is equal to the minimum of our rj and 1 over 2 beta gamma j. And then if you recall, r and gamma are related to the Lipschitz constants for the Jacobian, if you will. Okay, all right, so anyhow. All right, so for all x hat k, right, which are the ball of radius epsilon about x star, right, the Newton vector eta hat k, or eta k hat, right, which is the inverse of the Jacobian, right, applied to the vector field evaluated at a point xk is well defined. Okay. All right. So, all right. So, what other things do we use? Right. So, since R is a retraction, okay. thus a smooth mapping. And x star hat is a 0 of C hat. It follows that there exists some radius r, which I denote by r sub r greater than 0, and gamma r greater than 0. Again, these are going to be Lipschitz type things, such that, so this is, as you might expect, it's a Lipschitz estimate on the retraction now. Okay, the norm of the retraction applied to two different vectors. Okay, so actually I'm comparing the retraction, if you will, to sort of just the sort of, if you will, it's like the the Euclidean retraction, if you will, which was used to define the classical Newton method, right? Thanks. Okay. So I'm comparing this retraction with this other thing, right? And I want this to be less than equal to gamma r times the difference between the distance between the point xk hat and x star hat squared. This has to be true for all xk hat in a ball radius r about x star. Okay, and there's there's a little bit of a justification for this. It's like, but I won't go into too much of the details. But suffice to say, it's like you can do this, and more or less, it's a combination of So the reason why this holds is because basically of the rigidity property, if you will. Okay, so the reason why you can get an estimate like this is coming from the rigidity property. Okay, so this sort of comes from the local rigidity property. Okay, so I'm going to define a gamma hat. X hat, C hat. So this is like a transport, if you will. Okay, and again, this is the way to sort of think about this is that we're going to look at the difference between these two operators, because if you recall, you know, you have this of course shows up in the classical Newton method, and this shows up in the geometric Newton method. So I'm going to have some expression which tells me the difference of how they behave, if you will. So it's maybe transport operators a bad way of thinking about this is really sort of like the difference, if you will, between these two operators. Okay. All right. So then again, it's like as before, it's like you're going to find certain r's and gammas. It's like which are going to be Lipschitz constants, right? Again, by smoothness. Right, there exists r gamma greater than 0, gamma gamma greater than 0, such that the difference between these two things, that's two slightly different points, x hat and y hat, right, is less than or equal to gamma gamma multiplied by the distance between x hat and y hat. Okay. All right, so all this is sort of fairly straightforward, and then this has to be true for all sort of x hat and y hat, which are within a ball of radius r gamma about x star hat, right? And then, so there's a uniqueness to the connection at critical points, right? Right, then this gamma hat at x star hat, because c hat is equal to 0. Okay, and so this estimate, so it has to be that all right. So what I'm going to do is I'm going to let one of the points essentially be x star hat, right? So that then gives me an estimate for just x hat gamma hat x hat, because c hat, right, is less than or equal to gamma gamma difference between xk hat. So I should have a xk here minus x star. Right, and this is true for all xk hat in ball of radius epsilon, okay, around x hat star. Okay, so we need a Lipschitz constant. For d of c hat, right? So d c hat at x hat minus d c hat at y hat is less, okay, minus this gamma this is less than or equal to so I'm going to look at the difference of these two operators. All right, by the definition of gamma, right, that's going to be related to the Jacobian. Okay, so this is by definition equal to the Jacobian. Okay, and then of course this thing we have an estimate for, which is less than equal to gamma j x hat minus y hat. Then from the update algorithm which we had, which I should probably write down, right, xk plus 1 hat is equal to the retraction applied to minus j hat xk hat inverse applied to cos c xk with all the hats, right? Okay. All right, so by this definition, we can then say something about the rate of convergence, right? So we want to compare xk plus 1 hat minus x star hat. Okay, this is equal to, we're just going to apply that method to write it in terms of xk hat there's also the vector field minus x star hat. Okay. All right, so I'm going to leave this up here, and then I'm going to write down what that is in terms of a bunch of estimates, which we've been developing. Okay, so the norm of xk plus 1 hat minus x star hat, right, is less than equal to, okay, the norm of x k minus j xk, well, right, inverse times so what I'm doing, if you will, is that I'm replacing the retraction by this sort of the linear shift, right, which is this linear shift map, okay, and then the error is obtained by using the Lipschitz constant for the retraction, okay, so plus gamma r times the difference between xk hat and x star hat squared. All right. Okay. And then we're going to pull out a inverse of the Jacobian. Okay, so this is less than equal to j hat xk hat inverse applied to so I should mention, of course, that the vector field at x star is 0, so it doesn't hurt to add that term here. So that's what I'm going to do, right? So that's 0, if we will, right? This is 0, right? And then I'm going to subtract off. It's like, so I pulled out a factor of this inverse, right? So there's just left of this, c hat xk hat. And then these didn't have inverse, didn't have j acting on it, so I have to multiply it by j. It's like in order to cancel out the j inverse outside. Okay, so minus j hat xk hat applied to this. Okay. All right, so that's just for this first term. I still have the second term as before, so let me just add that plus gamma r xk hat minus x star hat. Okay, that's a square. All right. So I can write this norm of this thing. It's like in terms of the norm of the operator, it's like times the norm of the vector, right? So this is less than equal to the norm of the operator times the norm of the vector. Sorry. Okay, but I'm going to do one other thing, which is to change this to from j it's like to d, and the reason is because then this is going to allow me to use the estimate for the classical Newton method. Okay, but in order to do that, I also have to add a term which has to do with the error by replacing j with d. Okay, so all right, so let me just do that. Okay, so that's d c hat. All right, and if you recall, it's like this, the difference between d and j applied to a vector is given in terms of the gamma. All right, so there's a term plus, again, norm of this, the operator norm of the inverse of the Jacobian applied now to gamma hat xk hat c hat x star minus, okay, so I think this was an x star and this was an xk, x star minus xk. Yeah. Right, this was also an x star minus xk, sorry. Okay, all right. Okay, and then there's one more term again. It's like from the retraction. Squared. All right. Okay, so we're about ready now to use all the estimates we've established for this. So this is going to be less than equal to 2 times beta times 1/2 gamma j plus gamma gamma multiplied into the norm of xk hat minus x star hat squared plus 2 beta gamma gamma xk hat minus x star hat squared plus gamma r xk hat minus x star hat squared. So you'll see that we can sum up all these constants. It's like, and what will happen on the right hand side is basically some large constant multiplied by the square of the difference between xk, it's like an x star, right? So that's showing you that you have this quadratic rate of convergence, right? And this is true whenever this difference is less than or equal to the minimum of epsilon r gamma and r r gamma and r, right? Okay. All right, so this completes the proof. So this shows that the geometric Newton method, which we've been discussing, has this quadratic rate of convergence. Okay? All right, so let me just stop here for now.